Oh, thank you for checking out Fhenix. We're sponsoring a 5K bounty, so please pay attention to this workshop. And if you have any questions, feel free to message me directly. We're going to have documentation everywhere, so if you want to kind of pause the video to get some of the QR codes or the links, feel free to. But yeah, other than that, let's just get started. So what is Fhenix exactly? So we're basically building an L2. We're trying to add the ability for developers to add FHE operations to their smart contracts directly via FHE. And so we're the first blockchain to support general FHE. Real quickly before we dive into everything, here's a quick cheat sheet. Feel free to pause the video, go to this link. It'll basically set you up with all the good tutorials and documentations that you'll need to work with the network. It's pretty comprehensive, but if you run into anything specifically, feel free to reach out to me. There's also, like I said, YouTube videos I will go over and walk through the steps step by step. So as FHE. FHE stands for Fully Homomorphic Encryption, which is kind of a fancy name for being able to run arithmetic expressions over an encrypted field or operations over ciphertext, or basically you can kind of think about it as, I like to think about it as doing some sort of operations, computation, logic without having to decrypt something. So basically you can change the state of a network without revealing how the network has been updated. So homomorphic encryption is basically do some stuff on encrypted data. Basically what you do to A should happen to B. There should be some sort of relation there, hence the homomorphic. And fully homomorphic encryption is basically being able to do multiple operations over and over and over again. So arbitrary computation, technically speaking. In a way that homomorphic encryption uses this thing called noisy encryption, which means you're adding noise to kind of hide or encrypt the state of your plain text to make it private. And in order to do this, you need to run multiple operations in order to achieve a more complex state. However, the noise will compound, and hence we have this process called bootstrapping. But anyways, that's a little bit more technical than is really necessary. So I'm sure most of you are familiar with FHE versus ZKP. So ZKs are the more common way of adding privacy, or at least that's the narrative, security, an encrypted state in Web3 right now. However, FHE is kind of adding another element to this, while ZKs are mostly good for point of attestation privacy. It's kind of difficult to create a composable state since that the state isn't really stored on chain, and interacting with these things, these different states usually require some sort of decryption. So, you know, if you go to your favorite ZK privacy network and you try to figure out how to run a query on an encrypted field, you know, if you want to sort, if you want to look at the IDs, if you want to drill into something, have more complex logic, it's very difficult to do that because you can't really run operations without decrypting. But once you decrypt, you leak everything to plain text, and that kind of defeats the purpose of an encrypted network. As you can see, FHE currently has scalability issues. It is slow to some degree, slower than most operations. However, this is rapidly evolving almost by the week, and throughput is increasing like you almost won't believe. Composability also is great with FHE, as we'll go on a little bit later. But basically, you know, allowing you to add an encrypted space to your Solidity contracts or your contract state, if you would, is kind of this new novel introduction that Fhenix is bringing. And again, this is completely on chain versus like where ZK, mostly you're doing some of the private ZK stuff off chain, or using more of a complex like system of different pulls and levers, if you would, and then you're just kind of submitting the proof on chain. So that's the nice thing about FHE, is it's more in kind of the ethos of what blockchain stands for in terms of on-chain operations. So real quickly, a contract import, we're not trying to reinvent the wheel here. We want to make it as simple as possible for you guys to pick up what we're trying to do. So basically, if you just import FHE, as you see up here, you can kind of just interact with our library and your smart contracts. So you don't have to pick up a new language. You can use the tools that you're familiar with. Speaking of tools that you're familiar with, I'm sure a lot of you are familiar with Hardhat. So if you would like to use Hardhat, we have a tutorial that will show you how to set up a local instance on your machine. And so this is probably the ideal way to do tests or to script out your tests if you want to build more complex applications. But there's also a Remix plugin for those of you that are more familiar with Remix. I personally like Remix because I'm a little bit more of a visual learner, and I think this helps me kind of figure out what I need to pass in, what I need to see, what's actually happening with the contract in terms of interaction. And like I said, so for both of these, we have tutorial videos that will walk you through step by step how to get set up. If you get stuck anywhere, feel free to message me. I'll try to help unblock you. So real quickly, inputs, I'm sure most of you are familiar with just passing in some sort of uint 32, uint 8, uint 256, for example, which, represents a number in your contract. However, with FHE, we're doing this thing called EUINT. So it's basically just an encrypted unsigned integer of 8-bit length, and there's 16-bit, there's 32-bit, larger bit integers will be added in the future. But basically, this is the form of a large ciphertext instead of an integer. And what is a ciphertext? Well, not to get overcomplicated, but a ciphertext is basically just really long hash. It's just a hash string, very similar to like a normal hash that you would see. And basically what we're doing here is that we're passing in this number, and then we're setting this number as an encrypted integer, and then we're applying that logic as we're going on. If you want more specific examples, we have examples on our GitHub and our docs. And basically here, there's our two ways that you can pass it in. One is more of a typecasted version, the first version where you see set output, and then set output bytes is general byte code that you can also pass in depending on your use case. So conditional logic does get a little tricky with FHE. I'm going to skip over this slide here because there's a better one after, but essentially you can see that the first example that we have right here using the if else, which is how we're kind of taught naturally conditioned as software engineers to kind of write our conditional logic this way. However, FHE is a bit like constant time code, which means you want to have a single path to avoid branching, because branching gets a little sticky with FHE. Due to, well, the way I view it is due to the deterministic nature of what the ciphertext is. It doesn't necessarily branch. It's the value is already kind of set. So as you can see, this is sort of a bad example, the one that pointed on the left, where if A is less than B, versus probably the better way to do it is do this a less than. So LT is an operation, and if you want more specifics on all the operations, that will exist on our docs. But essentially, we're using a selector function here, and the selector function, for those of you that might be more familiar with the FHE VM's version of the multiplexer, the CMUX, basically you're taking an encrypted Boolean here is less than, and then it's running down the path of A or B. So it's going to assign A or it's going to assign B to this EUINT8 to return value, if that makes sense. There will be more documentation on our docs, and if you have any specific questions, I would definitely recommend checking out sample contracts or messaging me directly. Require statements are relatively straightforward, so they have to be slightly different than they exist in current Solidity require, just due to the fact that if you want to continue to you want your contract to be able to revert without necessarily having to reveal the contents of that function. FHE requires a great way to do it. Conversion leakage. So conversion leakage is very important when we're talking about security. So I like to think about it that the two main things that we really want to avoid are decryption and leaking plain text to memory. And if you don't decrypt, then you avoid leaking plain text to memory. So basically, if it existed somewhere, there is a trace of it, right? So, and here's a really quick example, right? So if you think about how the contract state is transitioning from state for state, the initial thing that happens here is you're passing in an unencrypted integer value, right? And even though you do encrypt the integer value and proceed however you need to with the rest of your state, if you were to look back at this initial state transition, you would see that this unencrypted value is passed in. So this is what I like to call conversion leakage, or just, I guess, data leakage in general. And so if you would like plain text leakage, if you would, I think this is something that's very important to remain cognizant of if you want to create secure applications. So from a high level, what is FHEOS? So at Fhenix, here at Fhenix, we're basically trying to build a comprehensive suite of encryption products. So the FHEOS is currently a wrapper around the TFHERS library, which is maintained by Zama, which handles a lot of the FHE operations. If you want more information about that, it'll be in the docs and some of the differences between FHE VM and what we're trying to do here. But again, the underlying library is composable, such as it interacts with a threshold service network. Threshold service network is kind of like a multi-party key management network, which handles the threshold decryption. In the future, oracles will be called from there, etc. But I'll avoid going too deep into that. If you want more specific information, please check out the white paper. But from a high level, this is kind of what we're trying to build. And then we have this thing called Phenix.js implementation. It's basically a JavaScript library that you can import into your client that will allow you to easier interact with the ABI. So for example, as you can see, we were passing in ciphertext values. So if you wanted to pass in a ciphertext value 5, for example, here's a quick example. Also, there are docs for how to handle permissions, which is, speaking of permissions, what exactly are permissions? So permissions are basically, if you have an encrypted field and you want to be able to view the encrypted field, or you want other people to view the encrypted field, this is how you do permissions. I like to think of a really simple example as FHE poker, right? If we have our cards and we're playing, I want to see what my 2 cards are so that I know how to play my hand. And but I don't want you to be able to view what my cards are and vice versa. So this is basically a way that you can do it. And from a high level, permissions are basically, you can think about it as an extension of EIP 712. But in practice, as you can see here, we're passing in the permissions object, and we kind of have this modifier called only sender here, which basically checks to see if the message.sender, basically the person who's actually calling this function, has the correct key access to view the contents that they're trying to view. And so here's an example of permissions. It's very dynamically programmable, so you can really set up the conditional logic however you want. Quick example is how an ERC20 will have an address that maps to an encrypted integer value that represents the amount of tokens that you know, a certain address owns. Again, here's a really quick sample contract, not too busy. If you want to import permissions, there's documentation for that. But as you can see, we're not reinventing the wheel here. Like I said, we're really trying to make it so that Solidity developers can pick this up as frictionlessly as possible. You know, basically think of it as like superpower functions that you can add to your current Solidity developer suite without having to completely change everything that you're doing. And so come win our hackathon. We want to see what you guys can build. We think this is a great frontier. Yeah, obviously just submit your GitHub repo, and preference will be shown to projects that are able to integrate the complete Phenix stack, which does include a front end, ABI integration, ideally hosting, the whole 9 yards. So general runtime tips, if you guys want to see the specific operations, I would definitely check out the docs, but there's 2 main things to remain cognizant of when you're building with FHE. First of all is the operations themselves. As you can see here, addition operations are much simpler and less computationally expensive than something like a division operation. And so the actual type of function that you're calling is very important. And the other thing is the actual integer size, right? So if you're using an 8-bit integer versus a 32-bit integer, this is going to have huge ramifications for the actual runtime. So definitely make sure that you are cognizant of that. And here's a pro tip from one of our developers, core developers, is, you know, try using ChatGPT. It might be more helpful than you would think. You know, if you pass in an example and then you try being like, hey, you know, you pass in some of our example contracts and be like, hey, in this format, if I was trying to make a voting contract, how would I do it? It might not give you the exact thing that you're looking for, but it might kind of help you point in the right direction, or at least some sort of structure. And yeah, that's pretty much it. If you want, you know, if you want a more code-along example of what to do, one of our developers also set up a blind auction contract, which is really good to kind of get a high-level overview of sort of the nuances of building with FHE on Phenix. And yeah, and so my name's Kyle again, and if you do want to reach out to me, my contact information is up here. So please don't hesitate to reach out. And if you want to get started on these docs ahead of London, please let me know. Thank you very much.